So, what about the bonding in carbon dioxide? Well, we've got two oxygens, and of course our bonding possibilities for the oxygens is one double bond, show the lone pairs of electrons there, or two single, and I'll show the electron pairs like that. Carbon can have 4 single covalent bonds, 2 singles, 1 double, 2 doubles, or a triple and a single. So those are the possible combinations that we can have in terms of the bonding that we have. So let's just consider what we've got here. Well, we can immediately discount this carbon because we've only got 2 atoms of oxygen attached to the carbon, and we should have, or we'd need 4 atoms attached there, so that's no good. And in the same way here we should have 1, 2, 3 atoms attached to that carbon, so that's no good either. These two possibilities, you will notice, are attached to 2 different atoms in each case. So if we look at the oxygen, there's no way that that one will work because we need a triple bond attached to the carbon, and neither combination for the oxygens produces a triple bond. Excuse me. And if we've got a single bond there, well, that oxygen could bond to there, but what else would it bond to? Can't bond to anything else. So therefore we can discount that. We can therefore have here carbon with 2 double bonds, discount that one, and we're left with carbon dioxide, C double bond O, like that, double bond O, like that. Put the electrons on the oxygen to make it a Lewis structure, so we're showing all the outermost electrons in all the atoms there. So what happens when we have charges on atoms and we need to form covalent bonds with charged atoms? So now in this case, of course, if we've got a negative charge, we must have 1 extra electron. Of course, if we're just talking about 1 single negative charge on an atom here. If we have a positive charge, we must have lost an electron. Okay, so that makes sense. So that means that if we are have had an extra electron added, it must mean that we need 1 less covalent bond. To produce our compound there, because having 1 extra charge means that we don't have to share any extra electrons or any extra electrons for that atom. And if we take a positive charge, we obviously need 1 more covalent bond. Let's take a couple of examples. If we take, for example, oxygen. Now oxygen, as we know, has 6 electrons in its outermost shell. So we've got 1, 2, 3, 4, 5, and let's add an extra electron there. Now if we have a negative charge there, we're going to add essentially an extra electron there. Let's make that a little star, shall we? Like that. So there's our electron. Therefore we need only 1 more electron to complete the octet. So if we have a negative charge on the oxygen, it now has that sort of arrangement. So one covalent bond required with a negatively charged O-. On the other hand, we have a positive charge. Let's take nitrogen for example. Now nitrogen has 1, 2, 3, 4, 5 electrons in its outermost shell. I've done that a little bit wrong. I should have put one around there, but let's lose an electron. Let's lose one of those electrons, shall we? So we have 5 electrons there. Let's give it a positive charge like that, and that leaves us therefore with only 4 electrons. We're going to therefore need 4 more electrons to complete the octet with the N+ ion. So therefore we're going to need 4 extra electrons, 4 covalent bonds in that case. So let's consider the bonding in the ammonium ion. Now, as we've said a little bit earlier, nitrogen has 5 electrons in its outermost shell, normally requires just 3 extra electrons, therefore 3 covalent bonds to form to complete. On the other hand, we have a positive charge. We've lost one of those electrons. So nitrogen with a positive charge will only have 4 electrons, therefore requires 4 more electrons to complete its octet, and therefore will use all 4 of its electrons in covalent bonding. So there we have the arrangement for N+. Hydrogen, well, we've got 4 hydrogens. Each hydrogen is going to have 1 electron in its outermost shell, requires just 1 more to complete its full outer shell, giving it noble gas electron configuration of helium. So therefore it will form a single covalent bond, and therefore if we combine those, we can see that each hydrogen will latch on to a covalent bond with each of the nitrogen covalent bonds, and we will end up with NH4 plus like that. Now this is just one way of showing the covalent bonding in the ammonium ion. There are other ways which involve dative covalent bonds, but essentially they're just models, and they are always just describing as best as we can what we experience. So, bonding in the sulfate ion. Now, sulfur, of course, is in period 3. If I can spell, period 3 of the periodic table. Therefore, it has a 3D subshell. So it can actually expand its octet. It doesn't necessarily have to have just 8 electrons in its outermost shell. There's room for in its outermost shell. But sulfur, of course, has 6 electrons at the moment as an atom, and they're all those electrons. It could form potentially 6 covalent bonds. It doesn't always. Sometimes it forms 2 or 6 or possibly even 4 at times. So let's just consider what we have for sulfur for the sulfate ion SO42-. So sulfur is a bit of a mystery at the moment. All that we can do is say, well, how many bonds is that going to form? But we have also 4 oxygens, and we have essentially 4 oxygens attached each separately to that sulfur. So let's put those down there like that. Okay. Now if we have our negative charge on 2- charge on the on the oxygens. So let's put a negative charge on 2 of the oxygens like that. Now that means that this oxygen now has 1, 2, 3, 4, 5, 6, and the extra electron is from the negative charge is 7. It means it will only need to share 1 electron with the sulfur to form our single covalent bond. So it only requires 1 covalent bond. Same for the other one. The other 2 oxygens, of course, having only 6 electrons, they're going to need to share 2 electrons, and therefore they're going to be double covalent bonds. So that's our combination. So let's just put that together with the sulfur and see what we get. So we'll have sulfur, two oxygens with negative charge. Let's put all the electrons on, and 2 oxygens with double bonds. So how are the oxygens? The oxygens are fine. They each have their complete octet of electrons. So we have oxygen 1, 2, 3, 4, 5, 6, 7 of its own electrons because of the negative charge. This oxygen 1, 2, 3, 4, 5, 6, 7 electrons because of the negative charge. This oxygen 1, 2, 3, 4, 5, 6 of its own electrons. This oxygen 1, 2, 3, 4, 5, 6 of its own electrons. But they also have complete octets, because if we take that as a pair of electrons, we've got 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen has a complete shell of electrons when it shares with sulfur, and oxygen here 1, 2, 3, 4, 5, 6, 7, 8 for complete octet there. What about this sulfur? Well, sulfur has, as we've said, 6 electrons in its outermost shell, and can therefore potentially form 6 covalent bonds. This sulfur is sharing 1, 2, 3, 4, 5, 6 of its electrons. So it's sharing all of its electrons to form those covalent bonds, and when it's sharing them, it has 2, 4, 6, 8, 10, 12 electrons surrounding the central sulfur there, which it can do because, of course, it's got that 3D subshell, which can expand the octet. You're not necessarily confined to just 8 electrons there.